All right, let's take a look at the questions from checkpoint 11. So getting into integration now. So 4 parts here. First couple of parts are indefinite integrals. So we're going to need to take some antiderivatives. So for the most part, what we're doing here is we're taking all your derivative rules that we've spent most of the semester on, and we're learning how to, you can write what's going on, and we're learning how to undo them. So as soon as this wakes back up and gives me control, we'll talk about how to do that. Or maybe I just need to, no, there you are. Okay. So first thing I'm going to do for this first function is I'm going to rewrite this in a way that helps me set up the power rule. So 5x squared plus 4x to the negative 3 plus 1 dx. So just like with derivatives, if they're all added together, I can so when they're added together, you can take derivatives basically a term at a time. Same kind of story when you have antiderivatives or you're taking integrals. So I'm going to do the same thing here. So think about the way the power rule works with derivatives, and I'll just go ahead and write these down. So when you're taking a derivative, what does the power rule say you have to do? Well, step one is you multiply by the exponent, right? So this is when you're dealing with things that look like this, x to the power of n. Basically, you bring down that value n. So I'm phrasing that as you multiply by the exponent. Then what's the second thing you do? You decrease exponent by 1. So when we do an antiderivative, we basically we do the exact same 2 steps, except we do them in the opposite order, and we do the exact opposite thing. So now instead of going 1 then 2, I'm going to do 2 then 1. So decrease exponent by 1. Actually, I'm going to increase the exponent by 1. So 5x cubed. And then multiply by the exponent. Okay, well, instead of multiply by the exponent, I'm going to divide by it. So this right here is the power rule for differentiation for derivatives. What does the power rule look like for integration? Looks like this. I have x to the n, and that becomes x to the n plus 1 all over n plus 1. And I can basically do the same thing with the other 2 terms here. So this second term is going to become 4x to the negative 2 over negative 2. And then this is going to become, well, what's the power on x here? It's a constant. So my power on x is effectively 0. So that becomes x to the 1 over 1. And remember, when you're taking an integral, a definite integral, you always have this arbitrary constant. So don't forget that. So if we clean this up a little bit, what do we have? We should have 5/3 x cubed minus 2 over x squared plus x plus c. All right, so there's my first indefinite integral. Moving on to part 2. Can't really deal with that as is. So I'm going to do a couple of things here before I get to a place where I'm going to deal with this as an integral. So first thing I'm going to do is to kind of facilitate this for power rule. So I'm going to rewrite this as x plus x to the half times 4 minus x. And now there is a product rule for integration. You haven't learned it yet. You will in the next module or 2. But for now, I think even when you learn that, it'd probably be more efficient to just distribute this. So 4x minus x squared plus 4x to the half minus x to the 3/2. And I don't think any of those combine. So we can integrate now. So we have four terms all joined by either addition or subtraction. All kind of written in a form that's friendly for power rule. So I'm going to go ahead and do that now. So 4x, this becomes 4x squared over 2. X squared minus x cubed over 3 plus 4x to the 3/2 over 3/2 minus x to the 5/2 over 5/2 plus c. So what simplifies? First one simplifies nicely. 2x squared minus a third x cubed. 4 divided by 3/2 is the same as 4 times 2/3. What is 4 times 2/3? That's 6 over 3. So that's, no, it's not. 4 times 2/3 is 8/3. So plus 8/3 times x to the 3/2. And then minus 2/5 x to the 5/2 plus c. So that is probably about as simplified as I'm going to get for part B. All right, part C. Part C is, what am I integrating there? There's nothing there. So first of all, this is a definite integral. And what tells you that is that I have limits of integration here. But it looks like there's no function to integrate. So what you can kind of assume here is that I'm integrating 1. So what is the antiderivative of 1? That should be, we kind of did that exact thing before. That should be x. So the indefinite integral or antiderivative is x. But now how do those limits of integration play into this? Now what I'm going to do is this. I'm going to evaluate the antiderivative at both those limits and find their difference. So 11 minus 1. That comes out to be 10. And one thing you probably noticed, if it wasn't explicitly said in the lecture videos and the example videos for this section, is that one of the really major differences when you're doing definite integrals as opposed to indefinite integrals is what the results look like. When you take an indefinite integral, what you get is a variable expression, typically. What you get when you take a definite integral is going to be a real number, if that integral exists. I'm not sure if I actually, now that I've said that, I doubt that you've done any integrals that don't come out to a real number. We'll talk about cases later on where that might happen. Okay, so next one here. This one is a lot more explicit about what the function is we're integrating. So we're integrating this quadratic, x squared plus x plus 1. So, and one thing I'll point out, because in my experience, this is something that a lot of people who are just kind of starting out with integration forget to do. Whether or not you act on it, you're probably going to have this like temptation to, all right, plug in 3 and -3 into this thing and find that difference. You still have to take an antiderivative. That has to happen in this process. So let's do that now. So what is the antiderivative here? Again, they're all added together, so I'll go term by term. So that's x cubed over 3 plus x squared over 2 plus x. So now that I have found that antiderivative, I have to evaluate it at both these limits of integration. So let's go ahead and do that now. So this will be 3 cubed over 3 plus 3 squared over 2 plus 3 minus all this. Another thing I'll warn you about is that when you're doing a definite integral, you're always going to have to subtract whatever the result is when you plug in your lower limit of integration in your antiderivative. So if there are multiple terms like there are now, make sure you subtract off all of them. Make sure you have parentheses here. So this is going to be -3 cubed over 3 plus negative 3 squared over 2 plus negative 3. So let's clean this up a little bit. One thing I will put out is, like, you'll notice I didn't even write down the constant of integration for either part of C or D. Let's say that I did. Let me see what happens if I try to, like, shimmy that in here now. So let's say that I put that plus C in my antiderivative here. What would happen there? Then I would have a plus C when I evaluated this antiderivative at 3, and another plus C when I evaluated the antiderivative at negative 3. But I'm subtracting those. So no matter what my constant of integration is, it's going to be annihilated by that subtraction. So because that is going to happen every time, we kind of bypass that step when we're doing a definite integral and don't even worry about that constant because it's always going to fall off. Okay, so back to simplifying. 3 to the third is 27, divided by 3 is 9. Plus 9 over 2, plus 3, minus negative 27 over 3, so that's plus 9, minus 9 over 2, plus 3. So those terms cancel, and I think the other one's double. So what do we get? We should get a final answer of 24. All right, so that is all for question 1. Question 2. So we're given a couple, we have like this piecewise velocity function for a particle, and we want to know basically how far it travels. So one thing you should verify that I will not, is that if you're going to ask, if I'm asking to find the total distance traveled by this particle, is that you want to make sure that it always goes in the same direction. And what I mean by that is that you want to make sure the velocity is always positive, that it's not going backwards at some time, because if it goes out and back and out and back and out and back, then you have to use a lot more integrals. Basically, you have to use a different integral every time it changes direction. This is not happening in this case. In this case, the particle is really just moving forward the entire time. Or, in other words, the velocity is always positive. So how do I find this distance knowing that? If I want to find the distance, that's going to be equal to the integral of the velocity with respect to time. I have to do that in 2 different chunks, basically. So what's the integral from 0 to 10 of 4 plus 0.2 t dt? So what's the integral look like? That'll be 4t plus power rule, 0.2 t squared over 2. And now that I have that antiderivative, I'm going to evaluate it at 0 and 10 and find that difference. And actually, before I do that, I'm going to actually simplify a little bit. 4t plus 0.1 t squared from 0 to 10. Let's not smush that across lines. So equals 4 times 10 plus 0.1 times 10 squared minus something convenient, 4 times 0 plus 0.1 times 0 squared. So the right-hand bracket is 0. But what happens to the left-hand bracket? I get 40 plus 0.1 times 100. So that's 10. So for the first 10 seconds of the motion of this thing, it goes 50 meters. So how do I find, oh, am I done? No, I'm not done. So now I have to find this other distance. So I have to integrate across the next 10 seconds. So from 10 to 20 of -2, and on the fly, I'm going to go ahead and rewrite this in a way that makes the power rule easier to carry out. 800t to the -2 dt. So antiderivative is going to be negative 2t plus 800 t to the negative 1 over negative 1. And we're going to evaluate that from 10 to 20. Can we simplify a little bit? Let's do that. So this equals negative 2t minus 800 over t from 10 to 20. So negative 2 times 20. Actually, let's just write it all out. Negative 2 times 20 minus 800 over 20 minus negative 2 times 10 minus 800 over 10. So minus 40 minus 40 plus 20 plus 80. All right, so all told, what does this come out to be? This is going to be 20. So my total distance is going to be 70 meters. All right, finally, part 3. So I'm giving you a function here, m. Function m, what is this function? So x is the number of water bottles produced by some company, and m of x is the marginal revenue generated by the company in dollars per bottle. So part A is to find this value first of all. So what is m of 4,000? So first part of this is to basically plug in and get a value. So let's do that first. All right, make sure I did this right. All right, so the number I'm getting here is a very large negative number, negative 47,971,965. So what does that number mean? So that number means basically at this production value, they are losing money. So basically, yeah, they're losing money at a rate of almost $48 million per bottle at this production level. So that's what that value means. So now let's find this other value. What does this mean? If I want to evaluate this function, or not this function, this integral. Okay, so we're doing an integral. So let's go ahead and get a number for that integral first. So we've got to do antiderivative. So 35x plus 7x squared over 2 minus 3x cubed over 3 is going to be x cubed from 0 to 4,000. This is going to equal what? 35 times 4,000 plus 7 halves times 4,000 squared minus 4,000 cubed. One thing I'm going to say here is I'm going to take a shortcut. I can tell that if I plug in 0 for all these x's, all my terms are going to zero out. So I'm not going to worry about subtracting that off. So now, so what does this come out to be? This comes out to be 140,000. Plus 56 million. And this one's going to be bad. Do not like these companies' chances. Minus 64 billion. It's just scientific notation, this. All right, here's the number I'm getting. And I'm gonna, so minus 63, 943, 860,000. So around negative 64 billion. What's the number I found? Well, the number I've found says that this company is losing lots and lots of money. Basically, they have made and sold 4,000 water bottles, and in the process, they have lost 60, like nearly $64 billion. So yeah, hopefully this is not realistic for any company, especially companies selling something like water bottles, but that's what these numbers represent. And that is all for checkpoint 11.